I just wanted to thank all of the organizers for continuing this and also giving me a chance to tell you about how you can generate axionic potentials from magnetic monopole loops or elephant loops. So I have a bunch of little elephants running in circles. And so a lot of this work is motivated by a conceptual question about axionic physics. Throughout this talk, I'm going to say that theta is an axion and has a field space that is 2 pi periodic. And as usual, we think of this as getting a potential from some other sector in the theory that we integrate out. And because of this 2 pi periodicity, we get a effective potential that takes schematically this form, some scale that's relevant to the sector that we integrated out, times some coefficients that we often have no clue about, times some instanton type action, exponentially suppressed term whose rate depends on the instanton action, and then this nice cosinusoidal behavior. And this form has to be there because, the field space is a circle, has to fit on the circle, has to be single valued. So one of the main motivating question and the main conceptual question that a lot of this has come out of is trying to answer or understand what happens when we take the instanton action, when we modify this other sector of the theory so that the instanton action shrinks to 0. From this form, we might expect that there's something problematic about this limit in the sense that we no longer have a natural suppression or exponential suppression between these different terms, between these different Fourier harmonics. And so it seems like we're losing control of this effective description. It's becoming, unwieldy. It's becoming, hard to use because we have to add a bunch of terms, right? And so the conceptual question that motivates this work is trying to understand what's causing this loss of control. And for this seminar series in particular, this has quantum gravitational motivations in the form of the weak gravity conjecture, where it would be very phenomenologically interesting if we could take the axion decay constant, or the physical circumference of this field space, to be very, very large, but there's some quantum gravitational constraint that suggests that these instanton actions go to 0 in that limit. As we try and restore a global shift symmetry, this is a generic, or seems to be a generic quantum gravitational behavior. And so it's very interesting, at least to me, to understand conceptually what's going on with that. So this has a very natural analog in familiar examples where, let's say we have a single scalar field, let's call it chi1, and we write down an effective action. And generically, this effective action is going to have a bunch of higher derivative operators. And much like in our axionic case, if I start studying this theory in a regime of parameters at momenta that are roughly on the order of this scale m, this natural suppression, that multiplies these higher derivative operators, we say that this theory breaks down. It becomes unwieldy because, again, we have to include an infinite number of corrections in any calculation that we do. And, unitarity becomes like a tricky thing to figure out whether this theory is actually making nice physical predictions. So again, here, the theory is becoming unwieldy. It's becoming hard to use because we have to include an infinite number of corrections or a large number of corrections. But in this case, we know how to repair the theory. We know that the reason for this divergence is that there's a new degree of freedom appearing at the scale m, and we can fix our effective theory by introducing this new degree of freedom. So one of the things I want to tell you, which appeared in last December, is that a similar situation is happening for the Axion. When I take the instanton action, defined in an appropriate way to zero, the theory once again becomes unwieldy, like the theory became unwieldy up here. And we have to include an infinite number of corrections. But, or, similarly, the cause of these two divergences, or these two, problems, are the same. And here we said that the theory is breaking down because there are light states that we have to account for. And similarly, the theory breaks down here because there are light states that are appearing somewhere along the Axion's field space. And in particular, those light states appear somewhere along the Axion's field space at some points. And as long as I stick away from those points, I can still use this effective field theory. I just have to do a resummation or use a different basis of functions to talk about this effective potential. So I'm not going to go into a huge amount of detail with this because I've given talks on this before, and it quickly descends into like a lot of talk about convergence of Laurent expansions and stuff. But I just want to give you a flavor for why this is happening. When I'm losing this exponential suppression, I can start taking derivatives with respect to theta of this effective potential, which is usually defined as the logarithm of some Euclidean partition function as a function of theta, and I strip off the space-time volume to get an actual effective potential energy density. If I start taking a bunch of derivatives of this, there's going to be some derivatives that are singular somewhere along this field space. So a very simple example is this function here, where I have an L to the minus 5 polynomial suppression. This AL factor is L to the minus 5, and I have this exponential factor that I can dial to 0. And I see that the effective potential itself, as I change this instanton action, barely changes at all. Like I don't know about you, but I can't see the difference. I didn't fake this either. Like all I did was to rescale the potential. So the actual effective potential is changing very little. But this loss of exponential suppression is showing up in some high order derivative. So the loss, this instanton action going to 0 is just telling you that somewhere along your Axion's field space, I have some singular derivative that the Fourier expansion that I've chosen to write my effective potential as in terms of cannot represent without having this loss of exponential suppression. It's just a general fact about Fourier series. And so what we should understand, how we should understand the appearance of these singularities or the appearance of these diverging derivatives is in terms of some excited states becoming light, some energy gap closing. This effective potential has to have singularities somewhere in the complex domain. And as I'm taking the instanton action to go to 0, these singularities are pinching on the Axion's field space. And that's causing this loss of control. And we can understand the fact that these singularities are causing this loss of control, and these singularities are due to excited states, by noting that this effective potential is going to inherit a singularity from the partition function whenever the partition function has a 0 or a pole. And just by writing the partition function in terms of, the energy eigenstates of the theory, we can see that I can get a 0 if an energy gap closes. Okay. So this is a general fact about axionic effective potentials. So that their convergence properties are determined by light states in the theory. And I can have a large energy gap as long as I can have a good effective theory with a divergent instanton expansion, as long as I stick away from where this gap closes, right? There's no breakdown in effective field theory there. So instead of thinking about just instantons generating this axionic effective potential, we can think of these instantons as like an avatar of these other states in the theory and these instantons are encoding their behavior in some way. But when my instanton action is going to 0, I shouldn't think about instantons anymore. I should think about the behavior, the properties of these light states, and I can express my effective potential in those terms. So statements like the axionic weak gravity conjecture, which are describing the behavior of the theory as these instanton actions are going to 0, can be re-expressed in terms of the behavior of energy gaps. And so I can remove this quantum gravitational conjecture from the framework of these instantons, which is kind of breaking down in this limit, and re-express it in terms of physical terms, in terms of energies of these states. So that was the main motivation, or at least the swampy motivation for understanding, for what I'm going to talk about now, which is trying to answer this other question, which is what other types of states can generate an axionic effective potential. If I said that instead of talking about instantons, I can think about states, as determining the effective potential. And what we want to understand is how we can use states. I tell you the properties of these states, how I can use those states and that information to get an axionic effective potential. And in fact, what the rest of this talk will focus on is understanding how and why loops of magnetic monopoles, virtual magnetic monopoles, can generate an axionic effective potential, even in theories that don't have or don't support instantons. Okay. And as I'll describe, this is an inevitable consequence of magnetic monopole physics. Everything that I'm going to talk about only relies on general gauge kinematics, the general properties of gauge theories and how they interact with magnetic monopoles. So perhaps the most important effect and the reason why magnetic monopoles can generate an effective potential for theta, for the axion, is the Witten effect, which is a general fact about magnetic monopoles in the presence of a theta angle. So one way of seeing the Witten effect is that if I take electrodynamics in the presence of an axion, we'll just take it as a non-dynamical axion, then Maxwell's equations get modified by a term that depends like this. So I can think of placing a magnetic monopole in a region where theta equals 0. So it's only emitting red magnetic flux. And then I surround that region of theta equals 0 with a theta equals not 0 region. And because of this jump, that's going to induce an electric charge around this at the interface of these two areas, or these two volumes. And so the Witten effect says that in the presence of a non-zero theta angle, a magnetic monopole acquires electric charge. And that electric charge is dependent on the theta angle and magnetic monopole charge. If you take that and you demand that the theta angle is periodic, that immediately implies that there's a tower of dions, a tower of these objects with magnetic charge and electric charge. And if you demand, and in general, this is the case, that the mass is natural in the sense of, I can estimate it by integrating the electric field energy up to the radius of the monopole, then their masses also depend on theta. So there's a general fact, the Witten effect, which is true just based on gauge kinematics, that implies that magnetic monopoles acquire an electric charge in the presence of a theta angle. And then theta periodicity implies that these magnetic monopoles automatically come within a tower. And then their masses depend on theta themselves because that's just how back reaction works. And so we expect that if we can somehow integrate out these magnetic monopoles, or this tower of dions, will generate a theta-dependent vacuum energy for the theory. And so we'll generate an axionic effective potential. So this can all be illustrated in the context of the Hooft-Polyakov model, or the Hooft-Polyakov monopole, which is embedded in the so-called Georgi-Glashow model, where I take an SU2 gauge theory and I break it down to a U1 by some adjoint Higgs. It's a three-dimensional vector, and this potential breaks the symmetry down to a U1. This permits a monopole solution, since SU2 mod U1, the second homotopy group of that is just an integer. And so if I look at the zero modes, if I look at the low energy theory of this monopole, its moduli space is R3, or R3 times an S1, and this S1 is coming from this unbroken U1. I can perform global U1 transformations on this monopole solution without changing it at all. And so its low energy effective theory looks like just a normal particle propagating in 3 spatial dimensions plus a extra circle. And this extra circle is responsible for the tower of dions. Its Fourier modes on the circle give me different charge eigenstates with different energies that grow as I change theta. And crucially, the quantities that this depends on are the mass of the W bosons and the mass of the monopole. This is the low energy effective theory. And so what we have are 2 different descriptions of the same system. For U1 gauge theory, I have either a tower of dions whose masses are linear, quadratically spaced, mass squared or quadratically spaced, and depend on theta. Or I can think about the theory as a magnetic or a new monopole with an additional collective coordinate, which I've called sigma. And the only 2 quantities that this depends on are the magnetic monopole mass and the spacing between these monopoles. Of course, I can add additional higher derivative corrections to this world line action. Similarly, I can add additional corrections to this mass relation, the relationship between the dion mass, the number in that, and the theta angle. But for the purposes of this talk, I'm just going to ignore the extra terms in red. And this turns out to be this mapping turns out to be exactly true for monopoles or dions that obey this match relationship, i.e. Dions, which are BPS. I have these 2 different pictures, and I can think of them as either requiring that I sum over dions because I have this tower of dions, or because this coordinate is periodic, I have to sum over windings. And these 2 pictures that I have are related via Poisson resummation, which is just a way of encoding this fact that I can either describe the system in terms of Fourier modes or describe the system in terms of winding.
And our expectation,
okay. And our expectation is that if we integrate out the system, we'll generate an effective potential for the theta angle because the mass depends on theta, or because this world line action depends on theta. So the picture that you should have in your head is we want to take a U1 gauge theory, let's say for simplicity, and incorporate the effect of these monopole configurations. Now, the way we do that is we think of these monopoles as defects whose world lines we have to sum over. And so instead of thinking about just the U1 gauge theory, we think about having a U1 gauge theory with a fixed monopole background and doing the path integral over that. So we extract the effective potential from this partition function, including all of these defects, where we've sum over all periodic configurations, which includes all periodic monopole world lines. And as is familiar from string theory, we can extract this partition function, at least when the monopoles weakly interact, by looking at just the probability of going from the one point back to the same point for a single monopole. So as long as these monopoles are weakly interacting, disconnected periodic paths dominate and exponentiate, and we get this relationship between the full partition function and just a single monopole world line partition function. And clearly, this monopole world, this world line partition function with S1 topology or circle topology determines the effective potential. So just to recap, maybe say a bit more simply, we want to include the effect of all of these monopole world lines in our theory as extra degrees of freedom. We're doing the partition function over all the different ways the theory can fluctuate, and that necessarily includes all of the different types of monopole configurations that we can have. And then the limit that these monopoles are weakly interacting, this computation simplifies, and we only need to pay attention to a single monopole propagating in the space-time. So with that in mind, we can write down our monopole world line theory. It only depends on two low energy parameters, the monopole mass and the monopole spacing or the dion spacing. And we can do this computation either thinking about integrating out a bunch of dions or including this collective coordinate. Either way, we find a general result for this axionic effective potential that's induced by monopoles. It has this form. And as I was saying before, it has it obeys this natural expectation that if I take the monopole mass to 0 and I have some light field that appears in the theory, if I close an energy gap, then the instanton action goes to 0. Now, very interestingly, if I just take the Hooft-Polyakov monopole and I plug in the monopole mass, which is 4 pi over g, and the monopole, there should be a v here, sorry, 4 pi v over g, and the dion spacing gv, I find that this quantity, this instanton action, is exactly the action of the BPST instanton. So we have two different pictures. At very low energies, we can just think about a U1 in the presence of magnetic monopoles. These generate an effective potential. But in the UV, if we have a UV description, we can also calculate the effective potential, in which case the instanton picture is useful. But this monopole-induced effective potential requires no UV description at all. We didn't need to know about any UV topology of the gauge theory. It only uses low energy data about these monopoles. And it could be that the theory that we have does not have some non-trivial topology. It's just a new contribution to the effective potential that people haven't found before. So with that, let me conclude. My main point is that instead of thinking about instantons as generating axionic effective potentials, we can think about it in terms of states. This gives a dual picture. It allows one to identify new sources of these potentials in terms of the properties of these states. And so as an example of this kind of general phenomenon that one can infer based on analyticity and convergence arguments of partition functions, you can find virtual monopole contribution to these axionic effective potentials, which takes this form. And usefully, it gives a new phenomenological ingredient for axion model building. So there's a bunch of future questions that we'd like to understand. How do we incorporate interactions into this picture? We assume that the monopoles were weakly interacting so that we could only consider one type of world line contribution. How do we include higher derivative corrections to this? In the paper, we gave arguments about why, at least in the regime that we were considering, these were suppressed and didn't affect the answer very much. But coming up with a systematic way of incorporating these higher derivative corrections would be very useful. Then a very interesting question is how these monopoles behave in the presence of light chiral fermions, which we know can very dramatically affect the behavior of this effective potential. And so that's work in progress that we're working on now. And then more generally, what other types of states generate an effective potential? Can we have a general apparatus for calculating these effective potentials in limits where the instantonic expansion fails? So with that, let me thank you. Thanks for listening.
Thanks a lot to John. So the first question will be by Craig.
Yeah, thanks for this nice talk, John. So I didn't understand this slide on the Witten effect. Mm-hmm. So the Witten effect basically tells you that in the presence of a theta angle, the Z2 duality between the magnetic and electric sectors is swapped. Is extended to be an SL2Z instead of a Z2. Now I can always, in every SL2Z duality frame, there exists an object which is charged only under the magnetic field, whatever that means in that duality frame. So I didn't understand this statement. Are you saying that there does not exist any magnetic monopoles?
I'm saying that if I have a theory with a let's say I have a theory with a single magnetic monopole, and I have a knob that's labeled theta, and I'm able to turn it. Then I'm saying that the Witten effect implies that as I turn that knob, these magnetic monopoles acquire an electric charge. So I'm not, when you phrased in terms of SL2Z duality, and I would have to think about that.
Yeah, I mean, I'm still puzzled about this statement, right? I mean, theta is a parameter of the theory, right?
Yes, yeah.
So if I have both a coupling and a parameter, I combine them into some, usual complexified coupling, and there's an SL2Z action, and under that action, basically you take an object which has charges Q and G under the electric and magnetic, and you act on that with some SL2Z matrix to form a new object.
Yeah.
So the reason I'm puzzled about this, for example, is the Witten effect is initially studied in like n equals 4 super Yang mills. And in n equals 4 super Yang mills, there are certainly BPS states which are only magnetically charged. So yeah, I was puzzled if you're really saying that there are only dionic states and no monopoles, although it sounds like it's kind of a more refined statement, although I don't quite understand.
So maybe I can try to resolve that. As far as I understood, John is just saying, take a monopole. As soon as you have a theta angle in your theory, you will generate automatically the full tower of dions. That doesn't mean that the monopole is absent, but whenever you have a monopole plus a theta angle, you have a full tower of dions, and that is effectively integrating out.
Yeah, okay. So basically the fact is you have a full, you basically have a complete spectrum under the SL2Z duality.
Yeah. Is that correct, John?
So
Yeah, I think so. I mean, maybe one way of saying it is if I look at the mass formula for these a general particle with electric charge and magnetic charge, that's going to depend on tau, this complexified parameter.
Sure.
And so it's going to depend on the theta angle. And that's really all I require here.
So maybe we allow for one more quick question, and the next person on the list is Tom, please.
Hi, thanks. Great talk, John. First, I wanted to make the comment that the Witten effect was not studied first in the context of n equals 4 theories. So yeah, I think John, what you were saying was right. But I had a question though, which was, so you made this nice argument that you can sort of replace the idea of instantons with states, with the energy of states when talking about the Axion weak gravity conjecture. I was wondering if this might shed any light into what the precise version of the conjecture is, since, as you know, there's usually when we talk about it, we have this squiggle. We don't have a sort of one constant. Also, I'm wondering if it might shed any light into actually being able to prove the conjecture, at least in some context.
Yeah, I think that's a great question. One of the things that I do not understand is when I wrote this formula, that was assuming a certain behavior of this energy gap. That, you know, this is saying that where the energy gap becomes minimal is theta star, and it's saying that the instanton action depends on the size of that energy gap. So it goes to 0 as the energy gap closes, divided by the susceptibility at that point. But in general, well, I'm not sure how often this is the case, but you could imagine that this is 0 at that point. And so this would have to, this then is replaced by a third derivative or fourth derivative, or, you know, so on and so forth. And so there seems to be quite a bit of flexibility in just changing this overall constant. If I think about this as like some normalizing factor, and I want to express everything in terms of this energy gap, that I don't quite understand what it would be about quantum gravity that would make a constraint on like the susceptibility at that point. So that would be a obstacle to coming up with a way to prove something like the axionic weak gravity conjecture in quantum gravitational theories. It's just why there would be a constraint on this thing, I have no idea. But in my view, the main problem that I had with this thing, not even the order 1 factor, but just this formulation in terms of the instanton action and a bound on instanton actions, is that as I'm taking F to become very, very large, the entire description that I'm using is breaking down. And so the instanton action, as you well know, is not a good guide to understanding the behavior of the theory in that limit. I think one of the benefits of rephrasing it in terms of this is not like description dependent. It just is, this is how the theory is behaving. So to answer your question, like it has a lot of, I think, conceptual benefits to rephrasing it like this, but there are more conceptual questions that become kind of obvious in this frame, why this should be the thing. But it would allow someone to check something like the weak gravity conjecture by going light state hunting. You try and find states that are becoming light as I'm trying to take a volume to be very big, which is kind of a very